Section 2, we're going to expand upon the probability rules, the addition rule, and complements. Objectives: use the addition rule for disjoint events. Use the general addition rule. Compute the probability of an event using the complement rule. Using the addition rule for disjoint events. What's a disjoint event? Another way of saying it is mutually exclusive. Two events are disjoint or mutually exclusive if they have no outcomes in common. Another name for disjoint events is mutually exclusive events. We often draw events using Venn diagrams. Using pictures represent events as circles enclosed in a rectangle. The rectangle represents sample space, and each circle represents an event. The point of these Venn diagrams is simply to try to bring order to chaos. It's just a pictorial way of representing events and how they relate to each other. For example, suppose we randomly selected a chip from a bag where each chip in the bag is labeled 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Let E represent the event. Choose a number less than or equal to 2. Let F represent the event. Choose a number greater than or equal to 8. These events are disjoint as shown in the figure in the next slide. In a Venn diagram, disjoint sets do not overlap since they have nothing in common. Notice we have the S here to represent the sample space. The events themselves, they have E within the circle, F within the circle, the S is within the square. Sometimes I've seen S outside, like something like this. The sample space is flexible as to where you put the label, but in general, for the events themselves, they are labeled inside the circles. Event E are all the figures that are less than or equal to 2. Listing that off, the only ones that satisfy that are 0, 1, and 2. F is greater than or equal to 8. All the figures that satisfy that event is just 8 and 9. The probability of E is going to be 3 over 10, since there are only 3 elements in E, and 10 from the entire space, 0.3. The probability of F, the number of elements in F divided by the number of elements in S, 2 over 10, or 0.2. Because there are only 2 elements in all of F, and then divided by the total number of elements within S, so 2 over 10. The event E or F, an event that falls within to E or F, could be one or the other. It is possible for it to be both, but we'll get into that. At the moment, E and F are disjoint. The probability of E or F, that's going to be the number of events in E or F, which is 5, the 0, 1, 2, 8, and 9, divided by the number of elements in the sample space of 10, so we have 0.5. Alternatively, note that N of E or F is the 3 plus 2 is equal to 5. Alternatively, P of E or F is equal to the probability of E plus the probability of F, which is 0.3 plus 0.2 is equal to 0.5. The addition rule for disjoint events is that if E and F are disjoint or mutually exclusive events, we have the following: P of E or F is equal to P of E plus P of F. The addition rule for disjoint events can be extended to more than just 2 disjointed events. in general, if E, F, G, H, I, J, K, L, M, N, O, P, etc., have no events in common, that is, they are pairwise, then we have the following. The probability of E or F or G or H or etc. is equal to the probability of E plus the probability of F plus the probability of G, etc. Note, pairwise disjoint just means that for any two sets that you pick, E and F, E and G, F and H, G and K, whatever the case may be, any two you pick, they will have nothing in common. We have these three sets. They are pairwise disjointed. P of E is going to be 3 over 10.3. P of F, number of elements in F divided by number of elements in S, 2 over 10 or 0.2. These are the same E and F as earlier. We now have this new set called G. The probability of G is going to be 2 over 10 or 0.2. The probability of E or F or G is going to be the probability of E plus the probability of F plus probability of G. That works the other way too. The number of E or F or G or the number in S. You just add up 3 from the E, 2 from the G, 2 from the F, all over 10. So we get still 0.7. Example number 2, Benford's law and the addition rule for disjoint events. Our number system consists of the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Because we do not write numbers such as 12 as 0, 1, 2, the first significant digit in any number must be 1 through 9. We may think that each digit appears with equal frequency, so that each digit has 1 over 9 probability of being the first significant digit, but this is not the case. In 1881, Simon Newcomb discovered that digits do not occur with equal frequency. The physicist Frank Benford discovered the same result in 1938. After studying lots and lots of data, he assigned the probabilities of occurrence for each of the first digits as shown in table 5 in the next slide. Here's table 5. Notice that 1 has the largest likelihood of occurring, then comes 2, and then it starts to decrease significantly down to less than 0.05. The probability model is now known as Benford's law and plays a major role in identifying fraudulent data on tax returns and accounting books. It does have a real-world use. Find the solution to each, verify that Benford's law is a probability model, use Benford's law to determine the probability that a randomly selected first digit is 1 or 2, then use Benford's law to determine the probability that a randomly selected first digit is at least 6. Please note in each case, randomly selected first digit. First digit. The first digit will never be 0. Some people might think, Mr. Armour, what about the 0.1? This or anything like it does not count. First digit does not count. This 0.1 or anything like it does not count because dropping the first 0 does not change the value. Technically, that is true with anything like these. What about the next 0? No, that doesn't count either. So, this here is just for convenience. So that is just to bring out that there's a decimal coming up. These are just placeholders. These are just to signify that these places have nothing in them. So yeah, zero doesn't count in Benford's law, no matter what. This one will be counted as the first digit. So even with decimals, the zeros don't have any place. Verified Benford's law is a probability model. Number one, each probability in table 5 is between 0 and 1. Check. If you look at the sum of all these probabilities, they all add up to 1. So because rules 1 and 2 are satisfied, table 5 represents a probability model. Those two rules, those are foundational. It doesn't get anything more complicated than that. Use Benford's law to determine the probability that randomly selected first digit is 1 or 2. Please note that a number can only have a single first digit. You can't have a number that has a 1 and a 2 as a first digit simultaneously. It's either one or the other. Because these are disjointed events, that's why I'm bringing that out. We can use the rule, the OR rule. P of 1 or 2 is equal to the probability of 1 plus the probability of 2, or 0.301 plus 0.176. So that gives us 0.477. If we looked at 100 random numbers, we would expect about 48 of them to begin with either a 1 or a 2. If we grab a newspaper or a magazine, or you look at a economics article online, and you look at all of those numbers and you randomly select 100 of them, we would expect about 48 of them to begin with a 1 or a 2. Use Benford's law to determine the probability that a randomly selected first digit is at least 6. That means the probability of at least 6, that's going to be 6, 7, 8, or 9. Those are the only things that satisfy that condition, at least 6. Since these are all disjointed events, mutually exclusive events, we can break that statement up into the probability of 6 plus the probability of 7 plus the probability of 8 plus the probability of 9. Add up all these numbers together and it gives you 0.222. We looked at 100 random numbers. We would expect about 22 of them to begin with either a 6 or a 7 or an 8 or a 9. Deck of cards and the addition rule for disjoint events. Suppose that a single card is selected from a standard 52 card deck, such as the one shown below. Just a standard deck of cards. Find the solution for each of these. Compute the probability of the event E, which is draw a king. And B, compute the probability of the event E, draw a king, or F, draw a queen, or G, draw a jack. Compute the probability of event E, drawing a king. The sample space consists of 52 cards. We have then N of S is 52. A standard deck of cards is 4 kings. We have N of E is 4. Therefore, we have this. The probability of E selecting a king is the probability, or it's the number of kings divided by the number of cards. So 4 over 52, which reduces to 1 over 13. And we'll just keep it at in this fraction form. Compute the probability of E drawing a king, F drawing a queen, or G drawing a jack. Standard deck of cards has 4 kings, 4 queens, 4 jacks. Because the events E, F, and G are all mutually exclusive, we are free to use the addition rule for disjointed events. extended to two or more. Not only are these mutual, these are pairwise disjointed. If we look at E and F, there are no cards that are both kings and queens together. So those are disjointed. E and G, those are disjointed. There are no cards that are both kings and jacks simultaneously. So those are mutually exclusive. F and G, those are mutually exclusive. These are pairwise mutually exclusive. We can use the addition rule for disjointed events extended to two or more disjointed events. So the probability of a king or queen or jack, that's going to be the probability of E or F or G, which breaks up into the probability of E plus probability of F plus probability of G. 4/52 plus 4/52 plus 4/52, which becomes 3/13. Likewise, all of these reduce to 1/13. So when we add these together, we still get 3/13. So doesn't matter how you cut it, 3/13. That addition rule applies when you have disjointed events. But what happens when you don't have disjointed events? And that's where this general addition rule comes in. Now you might think that, holy cow, another rule. Okay, no, yes, no. Here we have E and F redefined. Just for clarity, E is a collection of 1, 3, 5, 7, and 9. F is a collection of 0, 1, 2, 3, 4. All of these are odd numbers, and all of these are numbers that are less than 5. Because E and F now have something in common, that is 1 and 3, we show them as being overlapped. The 5, 7, 9, those are exclusively to E. So they appear in this circle and in the part of the circle of E that is not overlapped with F. So the 5, 7, 9, those imply these are exclusive to E. The 0, 2, and 4, the same thing. These are all exclusive to F. And because the 1 and 3 are common to both, they are shared by both, the 1 and 3 appear in the overlapped region. The overlap region tells you these are all the things that are shared by these two events. Anything that is in the set but not in the shared event, that means those elements are exclusive to that event. Now, we'll calculate this directly, compute by directly counting. So the probability of E or F is the number of elements in E or F divided by the number of elements in the space. So that gives us the 8/10. 8 because we have the 5, 7, and 9, so that's 3. The 1 and 3, that's an additional 2. And 0, 2, 4, that's an additional 3. 8 divided by 10, which reduces to 4/5. Notes, sample space is the 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Events E, 1, 3, 5, 7, 9. Events F, 0, 1, 2, 3, 4. The overlap region of E and F is 1 and 3. Now, if we try to apply the OR rule earlier, we get something strange. So P or E, using the earlier rule, we get 5/10 plus 5/10. Holy cow. Yeah, because the probability of E, that's going to be the 5, 7, 9, 1, and 3. All of those are in E, so that's 5/10. Well, that's the 13024 because all of those are part of F. So we get 5/10, which gives 1. There are two problems with the right side of this inequality. Looking at this closer, problem number 1, the 1 that we see at the end, this implies E and F covers the whole sample space. But when we look at the whole sample space, the 6 and the 8 in the upper left corner, but neither 6 nor 8 are in E or F. So yeah, so something's going wrong. Problem number 2 about this expression, P of E plus P of F is equal to 5/10 plus 5/10. Number 1, both E and F have 3 in common. So when we're looking at this 5/10 and 5/10, each of this 1 and 3 are being counted twice instead of once as they should be. These 1 and 3, they're being included in each of the 5s in the numerator. So the 1 and 3 in the overlap counted twice instead of once. When we're looking at the probability as a whole, we want each element to be counted only once. So there's a problem with using the earlier rule. So what we're going to do is adjust the rule. We have this overlapping region, E and F, that's the 1 and 3. The shaded regions represent E or F. What we're going to do is subtract once the overlap region. So E or F is going to be the probability of E plus the probability of F minus the probability of E and F. Everything that is common to both E and F. So we get 5/10 plus 5/10 minus 2/10 to give us 8/10, which reduces to 4/5, which is what we want to begin with. So 1 and 3 counted once here. 1 and 3 counted twice here. And then this part says remove one of the counts of 1 and 3. So they're counted twice. We remove once. So that lowers how many times 1 and 3 are counted. They're only counted once, just like all the other numbers. The 5, the 7, the 9, the 0, the 2, the 4. All of those were counted once. And with this adjustment, we now can say the 1 and the 3 are now counted once as well. Note, E and F overlap. Their overlap is counted twice in the term probability of E plus the probability of F. So the term minus probability of E and F is a corrective term by removing one of the double counts of the overlap. Note, the number of E or F divided by number in the space, 8/10 equals 4/5, which equals P of E or F. Here's the general addition rule. For any two events, the probability of E or F is equal to the probability of E plus the probability of F minus the probability of E and F. In the special case where E and F are disjointed, because they are disjointed, that means the probability of E and F is 0. Okay. They're disjointed. They have nothing in common. The probability of E and F is going to be the number of elements that are in both E and F divided by the number in the space which is going to be 0/10, which reduces to 0. 0/n of s, which still comes out to be 0. We start off with the general rule, and with the assumption that E and F are disjointed, they're mutually exclusive. That means this probability of E and F becomes 0, so we get P of E plus P of F minus 0, which reduces to this, our earlier rule. This general rule is truly a general rule. It applies to all cases, whether E and F are disjointed or not. If they happen to be disjointed, if they happen to be mutually exclusive, then that rule can be condensed by dropping that last term. Computing probabilities for events that are not disjointed. Suppose a single card is selected from a standard 52 deck. Compute the probability of the event E drawing a king, F drawing a diamond. So E or F. The probability of E or F is going to be the probability of E plus the probability of F minus the probability of E and F. The two happen together at the same time. So it gives us this. So the probability of king or diamond is the probability of a king plus the probability of a diamond minus the probability of king of diamonds, which is just short for saying the king and diamond. So we get this. The probability of king is this 4/52. The probability of a diamond, that's going to be this 13/52, since there are 13 cards in a suit, 13 diamonds, 13 spades, 13 clubs, 13 hearts. But there's only one king of diamonds. That gives us this 1/52. Since all the denominators are the same, we can just add up the numerators. 4 plus 13 minus 1, that gives us 16. Both 16 and 52, they have 4 in common. So that reduces to 4/13. Now, if you were to randomly select 13 cards, that means 4 of them should come out to be king of diamonds. That statement, randomly selecting a card from a deck 13 times, in this case, that means taking a card out, recording it, putting it back, shuffle it up, taking a new card out, look at it, record it, put it back, shuffle it about, and then doing that an additional 2 times. Because by taking the card out, if you don't put it back, you've now changed the probabilities. Because now, instead of 52 cards in the deck, now there's 51. That's why you have to put the card back in to maintain that 52. Reminder, king of diamonds is just short for king and diamond. Here's a table. Recalling chapter 2, section 4, table 6 is a contingency table or two-way table. It relates 2 categories of data. The row is marital status, because each row in the table describes a marital status of an individual. The column variable is gender. Each box inside the table is called a cell. The 46.0, that is inside a cell. The 11.9, that's inside a cell. The 12.1, that's inside a cell. The 3.1, that's inside a cell. Using the data in table 1 from the previous slide, determine the probability that a randomly selected U.S. resident 15 years old or older is male. Determine the probability that a randomly selected U.S. resident 15 years or older is widowed. And C, Determine the probability that a randomly selected U.S. resident 15 years or older is widowed or divorced. D, determine the probability that a randomly selected U.S. citizen is male or widowed. Now, to make this happen, it to be understood that these categories are disjointed. So never married, married, widowed, divorced, separated. To make this exercise work, males, females, those are disjointed. To make this exercise work, to drive home the point, per 4.4, we calculate the marginal distribution for table 6. We make table 7. So we add up each rows, we get a row total. Add up each column, we get a column total. By the way, and by adding up the totals, we get this grand total of 260.1. For part A, there are 26.9 million males and 261 million U.S. residences. The probability that a randomly selected U.S. resident is male is 126.9 over 260.1 to give us 0.488. Part B, there are 15.1 million residences who are widowed. The probability that a randomly selected U.S. resident is widowed is 15.2 over 260.1 to give us 0.058. Now, the key to this is that we are randomly selecting from all U.S. residents 15 years or older. That's why we choose to divide by 260.1. If you looked at all widowed people, if you limit yourself to just all widowed people and you ask yourself how many were male, that's going to reduce that denominator to the total number who are widowed. That divides into the total number within widowed who are male. C, assuming the events widowed and divorced are disjoint, we use the addition rule for disjoint events. The probability of widowed or divorced is equal to the probability of widowed plus probability of divorce, 15.2 over 260.1 plus 28.2 over 260.1. So they add up to 43.4 over 260.1, which gives us 0.167. So the probability of widowed or divorced is 0.167. Note, for the sake of the example, we're considering being widowed and divorced being disjointed events, non-overlapping events. In reality, they are not. It is possible for someone to be divorced and then widowed later on. Who knows? Maybe they got remarried or married again. Or a widowed person to be divorced. The events male and widowed are not mutually exclusive. In fact, there are 3.3 million males who are widowed in the United States, looking at the table. Therefore, we use the general addition rule to compute what is the probability of being male or widowed. The probability of male or widowed is the probability of male plus the probability of widowed minus the probability of male and widowed. So that gives us this 126.9 over 260.1, 15.2 over 260.1 minus the 3.3 over 260.1. Since all the denominators are the same, we can just add them up. That is, add up the numerators. So 138.8 over 260.1, so 0.534. Because the addition rule of disjointed events is only a special case of the general addition rule, one could conceivably use only the general addition rule without keeping the disjoint rule as a separate one. Some people want them to have separate, that's fine. If you can use just the general rule and remember that, hey, wait a minute, these are disjointed events, so that's third term drops out. Compute the probability of an event using complement rule. Please note, this rule will be heavily used in later chapters. It would be advantageous to get some understanding of this concept. But from my experience, it tends to be a difficult concept to grab hold of, mainly because people don't really think, never thought of it in that way. So let's dig into this. The complement of E, what is that? Let S denote the sample space of a probability experiment and let E denote the event. The complement of E, denoted as EC or E apostrophe, this is all outcomes in the sample space S that are not outcomes in event E. So you take your sample space, you look at event E, and anything that is not an E is part of the complement. Observations about the complement. Since whatever is an EC is not an E, that's by definition, then EC and E are disjoint or mutually exclusive automatically. Also, since EC is everything in S, note everything in S that is not in E, then the union of EC and E is S. By definition, EC is everything in S that is not in E. When we add E back into the picture, we now have S reconstructed. Now, if E represents any event and EC represents any complement of E, then we have this. We have sample space. We have event E. EC is everything outside of E. The entire region, the area outside. The probability of the complement of E is equal to 1 minus the probability of E. So that's another rule. But remembering those comments I mentioned back about that E and EC are mutually exclusive, and E and EC put together, they create the whole space. Complement rule. If we look at the general rule of OR, we have this. The probability of E or EC, that's going to be the probability of E plus the probability of EC minus the probability of E and EC. Remember what I said. The general rule of OR applies to any two groups. Doesn't matter if they overlap or not. But by observation 1, the earlier observation, since these are mutually exclusive, E and EC are mutually, that means the probability of E and EC is equal to 0. That brings us this. This P of E and C becomes 0, so we get this. So it disappears. Also, by observation number 2, that is, we take E, we take EC, we put them together, this or that recreates the entire space, the sample space. So we get this. The probability of E plus the probability of EC is equal to the probability of S, because E or EC is the sample space. The probability of S, that's the sample space, that's just going to be 1. The probability of E plus probability of EC, that's going to equal 1. And now subtract the probability of E from both sides. We get our formula. This is to point out that this formula, probably of EC is equal to 1 minus, that's not randomly created. There's a reason why it's that way. It falls out of this whole general rule of OR and the understanding that E and EC are mutually exclusive. And when you put E and EC together, you recreate the whole sample space all over again. Example, according to the National Gambling Impact Study Commission, 52% of Americans have played state lotteries. What is the probability that a randomly selected American has not played a state lottery? The probability of not played a state lottery, that's going to be either a person has played it or not played it. These two are mutually exclusive events. We put the two groups together, that will recreate, or that will, yeah, that will recreate the space of all Americans. So you pick any American, they either have played the lottery or not played the lottery. And we're told that 52% of Americans have played the lottery. What is the probability that a randomly, notice that word randomly selected American has not played a state lottery? Played and not played. These are not just mutually exclusive, they are complementary to each other. So the probability is 1 minus 0.52, which simplifies to 0.48. The probability that a randomly selected American who has not played a state lottery is 0.48. Data in Table 8 represents the income distribution of households in the United States in 2017. So less than 10,000, there were 7,800 households, 35,000 to 49,999, 15,248 households, 200,000 or more, 8,282 households. Compute the probability that a randomly selected household earned the following incomes in 2017 in each of the following scenarios. 1, 200,000 or more. B, less than 200,000. And C, at least 10,000. Now, for this, note that the total number of households is the sum of each of those items. We get 120,063. We'll need that for our calculations. For part A, this is rather simple. Part A, 200,000 or more. Remember, there are 120,063 households. Out of them, 8,284,000 earn 200,000 or more. So the probability earned of 200,000 or more is going to be this 8,284 divided by 120,063 to give us 0.069 rounded to the third decimal. 200,000 or more. The probability of randomly selecting a household that earned 200,000 or more in 2017 is 0.069. If we randomly selected 1,000 households in 2017, we would expect roughly 69 to have household incomes of 200,000 or more. So the 69, that's just 0.069 times 1,000 households to give us 69. B, less than 200,000. The long way is to add up all the households with incomes less than 200,000. So that's this 7,804 plus the 5,403 plus the 11,166, etc., all the way up to the 7,564. Add them all up, we get 111,779. So the probability of earned less than 200,000 will be this 111,779 divided by 120,063 to give us this 0.931. This direction, though, is time consuming and open to more errors because I have to add up all of these numbers. If I can avoid that'll be great. There's an alternative. The alternative is to recognize that the situations of less than 200,000 and 200,000 or more from part A are complementary. How do I know they're complementary? First of all, they don't overlap. Equally important, when you combine these two levels together, they cover all the income levels in the table. Any income level in the table can be represented by one of these two. Now, granted, less than 200,000 will cover all but one. That's fine. Since these are complementary, this is actually the preferred way. But with the caveat that you recognize that these are complementary events. That's why A was set up for B. Therefore, the probability of less than 200,000 is equal to 1 minus the probability of 200,000 or more, which is 1 minus 0.069, which is 0.931, the same value as before. This is not a trick as in coincidentally happen to be the same. No, it's a trick as in this is a shorter but equivalent way of doing it. The probability of randomly selecting a household that has earned less than 200,000 in 2017 is 0.931. If we randomly selected 1,000 households in 2017, we would expect 931 of them to have an income of less than 200,000. So at least 10,000. All the income that is at least 10,000. Note, the phrase at least can also mean greater than or equal to. The complement of at least 10,000 or greater than or equal to 10,000 is less than 10,000. 7,804 households earned less than 10,000. The probability of randomly selecting a household that earned at least 10,000 will be this. The probability of at least 10,000 is going to be 1 minus the probability of less than 10,000. So 1 minus 7,804 divided by 120,063 to give you 0.935. What I didn't have to do here, I didn't have to add up all of the households that satisfied at least 10,000. I just needed to recognize at least 10,000. Its complement is less than 10,000. And guess what? There are fewer levels that satisfy less than 10,000 than there are that satisfy at least 10,000. In fact, there's only one level that satisfies that. We just take that one, calculate its probability, subtract it from one. That gives us our. Now you could do it the other way, the long way, and that's fine. But that takes time and introduces more errors because the more numbers you have to add together, that brings in more errors as you're using your calculator. By the way, in this chapter, there'll be very little use for stack crunch. There will be towards the end of the chapter, but in these early sections, there won't be much use for stack crunch. Your calculator should be sufficient. The probability of randomly selecting a household that earned at least 10,027 is 0.935. Or if we randomly selected 1,000 households 2017, we'd expect about 935 to have household income of at least 10,000. That ends it for that. We'll see you tomorrow. Have a good evening. We'll see you tomorrow. Thanks.